Perfect. Made a mistake. There's a chemical spill here in Albuquerque. The only way to solve it is to determine the concentrations of 3 different acids along with their pH and their pOH by titrating them. What are we gonna do?
Okay. Alright, well, but before you get started, you need to know a couple things. Titration, is a controlled addition and measurement of the amount of a solution of known concentration required to react completely with a solution of unknown concentration. Because acids and bases react, the progressive addition of an acid to a base or base to an acid can be used to compare the concentrations of the acid and the base. And the equivalence point, you need to know that. It's the point at which the two solutions used in titration are present in chemically equivalent amounts. The endpoint, you also need to know that, of the indicator is the point in the titration at which the indicator changes color. Acid-base indicators are compounds whose colors are sensitive to pH.
Ugh. Yo, if only someone could help me. A bunch of acids and stuff. A lot of safety gear to wear, but don't know how to put it on.
I got you, buddy. Alright, so before proceeding with our experiment, the first step is to ensure the safety of all of our participating members. To start, we're going to start with the lab coat. And the next step is the sterilized gloves. It's the goggles. However, in addition to all of these safety equipment, there are also several dangers that we will be dealing with in the lab space. One of which, when dealing with strong substances such as strong acids and bases, we might have to use the eye wash station or the emergency shower, which is located across from me, next to the door. Also, when dealing with glass, you have to use a glass disposal located to the right of me. And that's our safety.
2 clean burettes were set up. It was decided which burette would be used for acid and which for base. The acid burette was rinsed 3 times with the acid that was used in the titration. The base burette was also rinsed 3 times with the base. The first burette was filled to a point above the 0 milliliter calibration mark with the acid. The approximate volume of 8 milliliters of acid was then flowed into a clean Erlenmeyer flask. The volume of the acid was recorded to the nearest 0.01 milliliters as the initial volume. Some acid was released from the burette to remove air bubbles. The initial volume was subtracted from the final reading. This was the exact volume of acid released into the flask, recorded to the nearest 0.01 milliliters. 3 drops of phenolphthalein was added to the flask. Some base was released from the burette to release air and lower the volume to the calibrated portion of the burette. The volume of the base was recorded to the nearest 0.01 milliliters as the initial volume. The Erlenmeyer flask was placed under the base burette, tip of burette extended into the mouth of the flask. The base was slowly released from the burette into the flask while the contents were constantly stirred. The pink color at the indicator faded with the stirring. When the titration neared its endpoint, base was added drop by drop. The equivalence point was reacted when a very light pink color remained after 30 seconds of swirling. After all of these steps were completed, Albuquerque had been saved, and the chemical spill had been cleaned up and solved.
I really needed this break after all that hard work. Alright, let's go and work on the data analysis now. Follow me. Now we're going to be moving on to our results for the experiment, starting off with acid A. Our formula with hydrochloric acid plus sodium hydroxide is going to yield water in addition to sodium chloride. So we did 3 trials with each acid. The results were pretty consistent for all of it. And the average volume we used for the hydrochloric acid was 7.98, and the base is 24.80. Following calculating the average volume, we put on the moles. We calculated that by using the formula N equals NV, converting that to the formula N equals MV. And then we found M and V. We were given M, which was 0.0195, and we multiplied that by the volume, which was 0.025 liters. And then that's how we found the number of moles used, which was 4.84 times 10 to the negative 4th moles of sodium hydroxide. And it's a 1-to-1 ratio from the hydrochloric acid to the sodium hydroxide, so it was the same amount of moles used for both. Moving on to the average molarity, we used the same formula, N equals N over L. So we divided the number of moles used by the liters of the solution, or liters of acid that we used. 7.98, converted that to liters, that was this number. And then that's how we got the molarity, which was 0.0602. And then we were given the molarity for the sodium hydroxide, 0.095. And then the average hydroxide hydronium concentration was 0.602. And then Over here it was 5.13 times 10 to the negative 13. To find the average pH, we did a negative log of the hydroxide concentration, which was 1.22. And with that, we were also able to calculate the average pOH, which was 12.8, and we got from that we got the OH concentration, which was 1.66 times 10 to the negative 13. And the same was done here. We used
Yo, it's your boy, Jake. We're doing science, acid B, hydrochloric acid. So my friend Parth already explained this. So first we use the average of the volume used, and then we use N equals M times B, and we got 2.18 times 10 to the negative 4th moles of hydrochloric acid. Then that's how we also used M equals N over L to get 0.0273 moles of hydrochloric acid. And then using all of that, we can calculate the average H3O ions and the pH, average OH ions, and just the pOH, and that's it, boo. See ya, peace, much love.
So, moving on to our third acid, sulfuric acid. We see over here on the base side, the average hydronium concentration, the average pH, the average hydroxide concentration, and the average pOH all remain the same as the two previous bases. The only change to data here is the average volume used and the average number of moles used, which is calculated by finding the average volume used converted to liters by dividing by 1,000, multiplied by molarity. Moving over here to the acid side, we find the volume used is similar to the other two previous acids, which is 8 milliliters. Over here in the number of average moles used, we take the number of average moles from the base and multiply by 1 mole of sulfuric acid over 2 moles of sodium hydroxide. This is due to the fact that there's a 1 to 2 ratio up here. This equals 1.01 times to the negative 4th moles of sulfuric acid. Using that number, we divide it by the number of liters for the average volume used, which is calculated by taking 8 milliliters divided by 1,000, equals 0.0126 molarity times 4. Using that number, we multiply by 2 because sulfuric acid is diprotic, meaning it has 2 hydrogens together. So that equals 2.52 times 10 to the negative 2nd. Using that, we come down here and take the negative log of that number equal the average pH. To find the average pOH, we subtract that number by 14, which equals 12.3. Using the 12.3, we take 10 to the negative 12.3, which equals 4.89 times 10 to the negative 13, which is the average hydronium or average hydroxide concentration.
Alright, right now we're comparing our data to the data of other cities that help with their chemical spills and how they save their cities. As you can see, the pH of our acid A was 1.22, which is very similar to the 1.20 average of the other cities. Our molarity was 0.0602, very similar to 0.0624. Moving on to acid B, our pH of 1.56 is very similar to the average of 1.54, meaning we did a good job with cleaning up our chemical spill. The molarity is 0.0273, very, very similar to 0.287. So far we did a great job. Moving on to acid C, our pH was 1.71, very similar to all these, close to the average of 1.67. Also the molarity for acid C was 0.0129, which as you can see is very similar to the other cities, and very close to the average of all the other cities. So I think we did a good job during our chemical spill.
It's all titrated, it's all done. I don't know how you did it, Mr. Abel, but it's perfect.
Wow. We saved Albuquerque.
Congratulations. That's what I'm talking about. Let's go, baby.
Mr. Abel, Mr. Officer, you have saved Albuquerque from the chemical spill.
Perfect. Yes, we did.
It seems as if we have made some slight errors. Let's go to Jake.
Got much time. Gus is coming in a little while. Error analysis. First, we got the impurities. You know, get a little water in them that doesn't get fully washed out. That could mess up the results. Then we got stuff like reading. We're human. We can't see down to the thousandths place. Could very much mess up the results, and then we don't get the perfect numbers that we're looking for. That Mr. Abel wants. And then lastly, the actual titrating. When you're going for that little pink color, you can go a little over on the base, you can go a little under on the base. That can affect the actual amount of base you put in, and that can affect the math later, making the results vary.